This is the teacher's summary for Unit 3, Lesson A, Similar Shapes. You want to go to your new reference card? We're going to review what are the basics of similarity. The slang version of similarity is something that has the same shape but a different size. That would be the basic definition. Same shape, different size, like small, medium, large, and some sort of clothing. The geometric definition is scare, which means similar shapes have congruent angles and ratios which are equal. Similar shapes have congruent angles and ratios which are equal. Similar shapes have congruent angles and ratios which are equal. S-C-A-R-E. Scare. So for example, in the shapes below, we see one that they have congruent angles. See, they have matching congruent angles. That's right. And then that's single. So we have congruent angles. That's the CA part of scare. And then let's look at the ratios. See if the ratios of the sides are equal. We have 15 and 6. 3 goes in there 5 times, and 3 goes in there twice. Let's check here. 20 and 8. 4 goes in there 5 times, 4 goes in there twice. So we have 5-to-2 ratios. And that means that would be ratios equal. That's the RE. Because of that, these two are similar. That's the symbol for similarity. And there's your S, similar. S-C-A-R-E, similarity. Now, because ratios are equal, then sides are proportional, which means the vast majority of the time, if you're dealing with ratios that are equal, you can use proportions, which looks something like this. So, bottom line is, if you have a proportion, you can cross-multiply, and that is about 80% of this entire unit, is the ability to use a proportion and cross-multiply. So some common proportions that we're going to use, and these proportions work in what's called the first dimension, which is the comparison of lengths only, is we can simply do side over side equals another set of side over sides. A common name for the comparison of the sides that are reduced to the lowest, that would be called scale factor. So for example, up here in this, when we took the 15 and 6 and reduced it, that would be called the scale factor, the side-to-side ratio reduced. Now, in your team projects, you also should have noticed that the perimeters reduced to the same ratio as the side over side. So another thing you could use is that if you take one side of a shape over the other side of a shape, that's going to reduce to the same ratio as the perimeter of the shape over the perimeter of the shape. Why? Because perimeter is also a first dimension measurement. So as long as we're in the same dimension, we can make these ratios. Write both those down, and I'll give you an example. Now, on a grid, on an XY grid, similar shapes are made by the process of what's called dilation. Dilation is what we use to create similar shapes on a coordinate plane. Dilation is simply changing in size. Change in size. We use this process to make things smaller or larger. So let me give you the formula, and then we'll do an example. This formula won't make a lot of sense until we do the example. So if you have x, a y coordinate, and you dilate by k. We use the variable k for the scale factor. In this case, k equals the scale factor. So if you have x, y, and you dilate by k, your new set of coordinates, all you do is multiply that scale factor by each coordinate. So you do x times k, comma, and y times k. Just remember this word, to change in size, just multiply. To change in size, just multiply. Say this with me. To change in size, just multiply. So when you dilate, you're going to end up with similar shapes. Let's do an example together. Go to your teacher example in your notes today. So here we are. We're going to use dilation, example 1, to change in size and multiply. And your scale factor, that's that factor k. Your scale factor, factor k, if it is greater than 1, we're going to make an image larger. If your scale factor is less than 1, it's going to make an image smaller. So sometimes it's a good idea just to visualize before doing a problem whether you are enlarging a shape or shrinking a shape. So let's do this example together. We are going to take this image and we're going to dilate by 5/3. So ask yourself this, 5/3, is it greater than 1? Or is 5/3 less than 1? And hopefully, since you realize that 3/3 is 1, we know that 5/3 is larger. So that means, this image here, we're going to make it larger. So first, let's get our original coordinates here. It says A, B, and C, but you don't know where that's at, so let's just find our coordinates. So here's coordinate A, and let's check. We are over 6 and up 12. So over 6, up 12. Okay, so our coordinates are here. We see that A is at 612, B is at 9, that's 9 and 6, and C is at 12 and 9. Let me just put the little coordinates here so you can see it. A is over 6, up 12, so you can see the blue, the green, and the red. We're going to take each of these coordinates and we're going to multiply by 5/3. To change in size, just multiply. Do not freak out with a fraction. This is really actually easy. Let me show you how easy it is. So we're going to take each coordinate. So we're going to take 6 and we're going to multiply by 5/3. And we're going to get a new coordinate. And we're going to take 12 and we're going to multiply by 5/3. And we're going to get a new coordinate. Okay, you ready? Just write those down. Now I'm going to take this super slow the first time. Okay, do this first one with me. 3 goes into 6. How many times? 2. So then I take that 2 and I'm going to bring it around to the 5. 2 times 5, my new coordinate is going to be 10. Let's do this again over here. Draw an arrow from 3 to 12. 3 goes into 12 4 times. Bring this little arrow around, put the little 4 there. 4 times 5 gives me 20. Let's do the next coordinates. That's 9 and 6. So here I have 9 and 6. We're going to times by 5 over 3, times by 5 over 3. Ready? 3 goes into 9 3 times. So I bring an arrow around, put the little baby 3 there. 3 times 5, 15. 3 goes into 6 twice. Bring that 2 around. 2 times 5, 10. Let's do 12 and 9. So here we have 12 and 9 times 5 over 3. Ready? 3 goes into 12. Do a little arrow. 3 goes into 12 4 times. Arrow around, little 4. 4 times 5 is 20. This one, do a little arrow, 3 into 9. 3 goes into 9 3 times. Bring this around. 3 times 5 is 15. So let's take a look at the results here. Our new coordinates for prime A is going to be 10 and 20. Our new coordinates for prime B is going to be 15 and 10. Our new coordinates for prime C is going to be 20 and 15. Let's plot those new coordinates. So it's 10 and 20. So there's 10 over 10 up to 20. There is my new prime A, 10, comma 20. B is going to be 15 and 10, so there's 10 again. And now I find 15, which is right between. So it's 15 and 10. So we go over 15, which is way out here, and then up to 10, which is right there. There is our sub B, which is 15, comma 10, sub B. And then C is going to be at 20 and 15. So over 20, which is way over here, and up to 15, we're right at the edge. There's our 15 right there. And that's our new C, sub C, which is going to be 20 and 15. Now, connect these. When you connect them, you should see two things. One, it should be the same shape, but just a different size. Same shape, but just a different size, which it is. It's a larger size, and we knew it was going to be larger because our scale factor was bigger than 1.